Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this lecture. We have been looking at creep deformation in the last two lectures of different class of materials and different mechanisms which governs this creep behavior. Today we will focus our attention to creep in polymeric materials, which also gives an idea about what happens to the non-crystalline or semi-crystalline materials during creep deformation. So in general, polymers show a much larger dependence on time and temperature than the metals and ceramics do. That is, polymers show creep effects at much lower stresses and temperatures. This stems from their peak van der Waals interchain forces. So we have a good background to realize all these effects, because we looked at polymeric deformation in tensile mode. Also, we briefly discussed about the polymeric structure, and we also know what is van der Waals force and all that. It's a secondary bond, right? So all this thing background will have a profound influence on their creep deformation. That's what it is. So as compared to metals and ceramics, these materials exhibit a larger dependence on time and temperature. Okay, we also looked at this time dependency of these materials in an elastic region. That also we have looked at it. In polymers, time dependent deformation becomes important even at room temperature. Two terms used to describe the time dependent behavior of polymers. One is creep, other is stress relaxation. In creep, one applies constant stress and the strain response is measured as a function of time. In stress relaxation, one applies constant strain and response is a decrease in stress as a function of time. So these two terms, a creep and stress relaxation, both are measured in this polymeric materials. We will just look at them and how their behavior is understood. That is also we will discuss in the lecture. For a glassy or viscoelastic polymer subjected to a constant stress, there is an initial elastic strain recovery followed by slow time dependent recovery. So that we are now talking about two terms. One is initial elastic strain recovery, that is instantaneous or immediate, followed by a time dependent recovery. So we have to distinguish these two things, and then we look at the total behavior. So in order to describe the creep deformation, people have thought of several models. So one of the popular model which most of the textbooks prescribes or describes is this kind of spring dashpot analogs. Okay, a spring is there and a dashpot is there with a viscous fluid and a piston kind of a thing which is attached to a spring, and then you apply a force like this, and the one end is fixed as it's shown here, that is called the spring dashpot setup. This is in a series, that means the dashpot and the spring are connected in a series, and in figure B it is connected through a parallel. So now you apply a force from this end and then try to look at what kind of stress or a strain experienced by the dashpot as well as the spring. So these two analogs are compared with the polymeric materials. We will see how. It's quite interesting, but then how much it is relevant to in real-time polymeric deformation. That is what we have to look at it. This viscoelastic response may be modeled as a spring dashpot in series, which is also called the Maxwell model, very popularly denoted as Maxwell model. In parallel is also called Voigt model. So it is instead of spring and dashpot in series and parallel, it is also referred as Maxwell and Voigt model as shown in this figure. An application of stress to this system results in a strain epsilon in the system. This strain is the sum of two contributions, and we can write epsilon is equal to epsilon 1 plus epsilon 2, where epsilon 1 is strain in the spring and epsilon 2 is the strain in the dashpot. So the strain experienced by the spring and the strain experienced by the dashpot can be additive because it is in the series. So epsilon is equal to epsilon 1, total strain is equal to epsilon 1 plus epsilon 2. The stresses in the spring and the dashpot are identical because the two are in series. So strain is additive, but the stress is equal, identical. They are not additive here. So this we have to understand for this model. Then we can write the following relationship for an elastic and a viscous case. So this is a basic Young's modulus equation. Stress is proportional to strain and sigma is equal to E epsilon. That kind of equation. You can rewrite that equation like this. For a viscous flow, this is stress is written like this: sigma is equal to eta times d epsilon 2 by dt. This is a gradient, right? This is the basic relations. We have already seen it, so we can make use of this to analyze this stress strain relation here. From the above equation, we can rewrite those like d epsilon by dt is equal to d epsilon 1 by dt plus d epsilon 2 by dt, which is can be rewritten as 1 by e times d sigma by dt from this relation plus eta, sigma by eta from this relation. So this we are replacing with these two terms, which is taken from the basic equations. So now note that the series or a Maxwell model does not correctly predict the behavior of a viscoelastic material under constant stress or a creep condition, where sigma is equal to sigma naught, because in this case the d epsilon by dt is predicted by this Maxwell model is equal to sigma naught by eta. That is, the Maxwell model for a creep or a constant stress conditions predicts that the strain increases linearly with time. That is shown in this figure. But most polymers, however, the d epsilon by dt or the d by dt increase with time. This is not the real time case. Okay, so we will see what is that Maxwell model can actually predict. The Maxwell model is more realistic in the case of a stress relaxation test. Okay, it is not predicting the creep behavior, but on the stress relaxation test it can predict how, during which we impose a constant strain, which is epsilon is equal to epsilon naught, then d epsilon by dt is equal to 0. So in the previous case it is increasing, but here it is 0. Under these conditions, equation can be written as, that is, d epsilon by dt is equal to 0, which is equal to 1 by e times d sigma by dt plus sigma by eta. This equation, it is there in the previous slide, and then we can rewrite them into this form. That is, d sigma by sigma is equal to minus e by eta times dt. So we can now integrate this, and then we get an expression for sigma, like sigma is equal to sigma naught into exponential minus et by eta. So the quantity eta by e is referred to as the relaxation time tau. So this relaxation time we have already looked at it in the anelasticity chapter. We discussed it, and there also we looked at how this term comes from the viscous viscoelastic behavior. So same parameter here, and we can rewrite this equation now, replacing this eta by e as sigma is equal to sigma naught into exponential minus t by tau. So this is a very standard expression now. Now we can see whether this is going to be useful. So what I have shown in this plot is the stress versus time and the stress versus strain versus time and stress versus time plot for the both the models, and whichever is obeying the actual behavior, that we can discuss then and there. Okay, right now we just said that Maxwell model does not predict the strain versus time behavior. On the other hand, stress relaxation behavior it is predicting. So that is what this equation shows. So okay, so equation says that the stress decays exponentially with time as shown in the figure B. So the stress versus time Maxwell plot, it is almost it is an exponential decay. Stress decay is shown here. So this is so this model is valid for the stress relaxation behavior. This is quite reasonable for many polymers. However, the process of stress relaxation does not go on infinitely in real material. So the model predicts that it goes like this. So if it is not touching the time axis, then it is infinite, right? So which is not the case in the most of the real time material. So that is one drawback with this Maxwell model. In another model called Voigt model, the spring and dashpot are arranged in parallel, which is shown in the figure. This means that the strains in the two components are identical. So there it was the stress was identical. Here the strain is identical. Our strains are identical. There it is a stress. So we can rewrite this, and the stresses in the two components add to give the stress on the system. That is, in a spring dashpot connected in parallel, the stress is additive. So sigma is equal to sigma 1 plus sigma 2. That is what the Voigt model assumes. So we can rewrite dot equation like we have written in the previous case. It is a very simple substitution. You can just look at the previous slide. It is the same. So we can rewrite this epsilon by dt is equal to sigma naught by eta minus E times epsilon by eta. Let us now examine the predictions of the Voigt model for a creep or a constant stress loading and for stress relaxation. For the constant stress situation, sigma is equal to sigma naught. Then equation has become d epsilon by dt plus E times epsilon by eta is equal to sigma naught by eta. So this is what it is. If you put this condition, this differential equation has the solution like this form. Okay, so whether that is predicting or not, that we have to see. Remembering that the quantity eta by is a relaxation time tau, we can replace that. We find that the variation in strain with time at a constant stress is given by epsilon is equal to sigma naught by E times 1 minus exponential minus t by tau. So this is the final expression. So what does this expression say now? This relationship shown in the figure, we will go back to the figure now. The prediction of Voigt model is quite realistic because when epsilon tends to sigma by E as t tend to infinity, this is what that plot also predicts. What is that plot? Now we'll go back to this plot. So this is the plot we are talking about, right? This is the plot we are talking about. So the Voigt model predicts the so for a constant stress relaxation case, we have an imposed constant strain, that is epsilon is equal to epsilon naught, and therefore d epsilon by dt is equal to 0. So for the constant stress, the Voigt model predicts quite realistic behavior of polymer. For the stress relaxation case, we have to impose this condition, that is d epsilon by dt is equal to 0. Then Voigt model predicts that sigma by eta is equal to E times epsilon naught, which is a linear behavior, right? Whether this is okay or not. This linear elastic response, however shown in this figure, do not conform to reality. So these two models are, predicting the and only one condition, either the stress relaxation or the constant stress or creep. These are the two models, but they predict only on the either one of them in the both the deformation cases. So what is shown in this plot, the molecular weight of a polymer can affect its creep behavior. So the strain versus time plot, you can see that with increasing the molecular weight, it is having some influence on the creep behavior, right? The strain response of the polymer as a function of time, that is, strain as a function of time, is shown in the figure. Also shown the effect of molecular. So strain is here, it's a constant stress, and then you can see the strain. And this is a strain versus time. So that's what it's shown here. The effect of increasing the degree of cross-linking is in the same direction as that of increasing the molecular weight. So the degree of cross-linking has the same effect like the molecular weight increase. So both are interconnected anyway. Both tend to promote secondary bonding between chains and thus make the polymer more creep resistant. So the higher molecular weight polymer will have better creep resistant. So that is what this these models explain. Compared to glassy polymers, semicrystalline polymers tend to be more creep resistant. Polymers containing aromatic rings in the chain are more creep resistant. Both increased crystallinity and incorporation of rigid rings add to the thermal stability and thus to creep resistance of a polymer. So these are some general characteristics. In a constant stress test of a kind just described, a parameter of interest is creep compliance, J. What is compliance? Compliance is inverse of E. That means ratio of strain to stress. Okay. This is the ratio of strain to stress. Since the strain will be a function of time, the compliance will also be a function of time. Thus, you can write like J as a function of T is equal to epsilon as a function of T by sigma naught. So this parameter is called creep compliance. From the above equations, we can use this, and then the previous equation, we can rewrite this the equation for the creep compliance, which is J as a function of T is equal to epsilon T by sigma naught, which is equal to 1 by E times 1 minus exponential minus T by tau. So what is now shown in this figure is the creep compliance is plotted versus time, but in a log scale. You can see that it's very interesting plot. We will try to explain this. A series of creep compliances versus time, both on logarithmic scales over a range of temperatures. So for a different range of temperatures, the creep compliance curves are drawn here, and one can build a master curve from these kind of experiments, and this is a master curve. One can build it from that. So how do you build this master curve? The individual plots in A can be superimposed by an horizontal shifting along the log time axis by an amount log AT to obtain a master curve corresponding to a reference temperature Tg of a polymer. You see, this creep compliance versus log time has this kind of a variation with the reference temperature Tg. Okay, in semi-crystalline or glassy material or polymers, Tg is a very important temperature, like our recrystallization behavior, right? In metals we talk about, ceramics we talk about, right? We were also talking about critical temperatures, recrystallization temperature and so on, right? So here in polymeric material, this is Tg is the reference temperature. So, but these plots are one over the other. To generate this kind of a master plot, to have an overall understanding, that is, we need some a constant that is called shifting constant. A shifting constant At is required. So if you shift each of this curve to by this constant At, then you get this kind of master curve. What does this master curve show? It shows that the polymeric deformation as a function of time, but it will now show the different regions like viscoelastic, rubbery plateau, and then complete viscous flow. So this kind of mechanisms, all the mechanisms are nicely revealed if you do this master curve construction. Okay, so we'll see a little more on this master curve. A very useful principle called the time temperature superposition allows us to take the data at one temperature and superimpose them on data taken at another temperature by shift along the log time axis. So this experiment is done to generate these kind of a master curve. So one of the models people have tried to plot this relaxation modulus versus time, and then you generate these kind of curve and then shift them by the method. Just we looked at it and you plot them, then you get this master curve like this. We will look at it. There are particular model which are used to obtain this the constant, the shifting constant. This principle is of great practical use in as much as obtaining data over a full range of creep compliance or stress relaxation behavior, which can involve even years, right? So, which is very important because when you say stress relaxation, that time is quite large, depending upon the material, what kind of material we are looking at it. So the stress relaxation in the context of stress relaxation behavior, this relaxation modulus is also very important parameter. The principle allows one to shift data taken over a short time spans but at different temperatures to obtain a master curve that covers long time spans. So you take data from short time and then extrapolate to a long time. So for that, Williams, Landell and Ferry found that the logarithm of AT, that is a time shift factor, follows a simple expression like this: log AT is equal to minus C1 times T minus Ts divided by C2 plus T minus Ts, where C1 and C2 are constants and Ts is a reference temperature for a given polymer. If we take the reference temperature to be the glass, the transition temperature is Tg, then C1 is 17.5 and C2 is 52K, something like that. So if the reference temperature is Ts is taken to be about 50 degree above Tg, then C1 is 20.4 and C2 is 101.6K. So these are some of the examples how this time shift factor is being adopted to arrive at a master curve in a relaxation modulus versus time plot. So what is shown here in C, in continuation with the previous slide, is a shift along the long time scale to produce a master curve, modulus versus time. The bottom one is experimentally determined shift factor. So one can also find the shift factor experimentally. So now we will come to one more important point. The Voigt model is used to explain the stress relaxation behavior of a polymer. That's what we have just seen, that Voigt model is useful, but it was not explaining the other parameter. We impose a constant strain epsilon naught and follow the drop in the stress as a function of time. So stress relaxation means what? You impose a constant strain and allow the material to relax and observe the stress. That is the stress relaxation. So instead of compliance term, we now have a stress relaxation modulus, which is given by E as a function of T, which is equal to sigma T divided by epsilon naught. In the case of stress relaxation also, one can obtain a master curve as shown in the figure. So this is a stress relaxation curve, typical stress relaxation at a constant imposed strain epsilon naught results in a drop in stress sigma as a function of T, and the master curve is shown here, typical master curve, log E versus log T. So this is relaxation modulus. A master curve obtained in the case of stress relaxation showing the variation in the reduced modulus as a function of time. Also shown is the effect of cross-linking and molecular weight. So these plots are very interesting because they have a complete practical relevance. We are talking about reduced modulus. That means as a function of, as the time passed by, the modulus relaxed. So it's called reduced modulus, right? So this is also a function of molecular weight and then cross-linking. So it's completely based upon the structural information, structural aspects of the polymer material. That's what we have to understand. Stress relaxation in polymer is of great practical significance when the polymers are used in application involving gaskets and seals. This is very interesting point we have to realize, and this in fact we observe in the day-to-day life. Gaskets and seals, they are, after some time they will lose their functionality. For example, the gasket in the pressure cooker, the seals, we use it in most of the simple boxes. People use with seals. They, after some time, that seal will become loose, or it becomes brittle, or it becomes first it will become loose. That means it has completely relaxed, right? At times, this effect can be exploited beneficially. How can we exploit this stress relaxation? That is another important and applied in the reality. For example, in a situation where the residual stresses are not desirable, we can incorporate a polymer to undergo easy stress relaxation in response to residual stresses. So this is very, very important. So if you have an issue with the residual stresses, then incorporating a polymer and then allow them to relax, that will take care of the effect of residual stress. So this is also very interesting application to realize the stress relaxation behavior of polymers.